going to talk about change of variables in multiple integrals. We have done change of variables in one-dimensional calculus. For example, the substitution rule, substitution method, which we briefly did as USUB in section 5.5. We did a change of variables. We let x equal to g of u, a function of u, so that dx is g power u du. So we did a change variable from u to x. Here x is correspond to g of u, and dx is corresponding to g power u du. And x go from a to b, u go from c to d. A change of variables can also be useful in double integrals, and we have already seen one example of this, which is the conversion from rectangular to polar coordinate in double integrals. At that time, we did a change of variables. We let x equal to r cosine theta, y equal to r sine theta. So x is being replaced by r cosine theta, y being replaced by r sine theta, and dA is being replaced by r dr d theta. When we do this double integral over a region on the xy plane, that is going to correspond to this double integral over a region in the r theta plane. For example, this region on this xy plane is a circle with its interior, and we can see that r in this case go from 0 to 1, and theta go from 0 to 2 pi. This region on the xy plane is corresponding to this rectangular region on this r theta plane. The variable r and theta are related to x and y in these two equations. More generally, instead of the r theta plane, let's consider a UV plane. So think about this r, it's a special case of u, and this a special case of v. So we consider a change of variable given by a transformation from the UV plane to the xy plane, where x is a function of u and v, just like this, and y is a function of u and v, similar to like this. Or we sometimes write this as x is x of u and v, y is equal to y of u and v, so that you can see that this gives you the corresponding x, this is going to give you the corresponding y. And we usually assume that this transformation from this UV plane to the xy plane is a C1 transformation. And what does it mean is the function g and h have continuous first order partial derivative. For example, the partial derivative of this function with respect to u and with respect to v are continuous. A transformation T is just a function that map a region S on the UV plane to a region R on the XY plane, where R and S are both subsets of R2. For example, this transformation map this point U1V1 in S to the point x1, y1 in R, x1, y1 is called the image of u1, v1 under this transformation. If no two points in this region S have the same image in R, then we call this transformation one-to-one. This R here on the xy plane is the image of this S, and it consists of the images of all points in S. If this transformation is a one-to-one transformation, which means there's no two points in S mapped to the same image, and if this transformation here is one-to-one, then this transformation has an inverse transformation denoted T inverse. Now, T and T inverse are inverse transformations. If we know T, how do we find T inverse? If we are given x equal to g of u and v, y is equal to h of u and v, how do you find T inverse? For example, we're given x equal to a function of u and v, y equal to a function of u and v, then we can solve for u and v, express u and v as function of x and y. This inverse transformation will be defined by this change of variables. Let's try one example. A transformation is defined by these two equations. Find the image of the square where u go from 0 to 1, v go from 0 to 1. We want to see the image of this S on this xy plane. So what kind of shape, what kind of region are we going to get under this transformation? In order to find this region on the xy plane that corresponds to this region on the uv plane, let's consider the boundary. The boundary of this S under this transformation is going to map to the boundary of R. So we're going to begin by finding the image of the side of this S, the boundary of this S, and we consider each side over here. So divide this into 4 sides. So step 1 is to find the image of the size of S. Let's consider this side of S, where u go from 0 to 1 and v equal to 0 along this side. Since x is equal to u squared minus v squared and v is equal to 0, substitute v equal to 0 here, x is equal to u squared. Substitute v equal to 0 here, y is equal to 0. Now, because u go from 0 to 1, x equal to u squared, x will be greater equal to 0 and less than equal to 1. So this side of S, let's call this S1, is going to be mapped into where this nice segment x is greater equal to 0, less than equal to 1, and y equal to 0. And let's call this R1. So S1 here on the UV plane is being mapped to this nice segment here on the XY plane. Next, we consider this side of S. Let's call that S2. Along this side, U is equal to 1 and v go from 0 to 1. So substitute u equal to 1 in this equation. We get x is equal to 1 minus v squared. And into this equation, we get y is equal to 2v. Now, because v go from 0 to 1, we know that x is greater than or equal to 0, less than or equal to 1, and y is greater than or equal to 0 and less than or equal to 2. Eliminate v in these two equations, we get an equation that relate x and y directly. The graph of this equation is part of a parabola. Let's call this R2. So S2 is being mapped to R2. Similarly, this side of S, let's call this S3. You go from 1 and end it to u equal to 0. And v along the side, v is the constant 1. Substituting v equal to 1 into that change of variable, we get s is equal to u squared minus 1, y equal to 2u. Because u is greater than equal to 0, less than equal to 1, s here is greater than equal to negative 1, less than equal to 0. And y is greater than equal to 0 and less than equal to 2. Eliminate the variable u from these two equations. We get an equation that relate x and y directly. X is equal to parenthesis y over 2 squared minus 1. The graph of this is this part of a parabola. Finally, for S4, from this point to this point, finally, for this side S4, from here to here, u is equal to 0, v is greater than equal to 0, less than equal to 1. Substituting u equal to 0 in the two equations here, we get x is equal to negative v squared and y is equal to 0. Because v greater than equal to 0, less than equal to 1, x is going to be greater than equal to negative 1, less than equal to 0. The graph of this is this nice segment, x greater than equal to negative 1, less than equal to 0, and y is equal to 0. Let's call this nice segment here R4. So S4 is being mapped to R4 on this xy plane. Step 2. Now we can conclude that the image of this S under this transformation is going to be this region R with the boundary defined above. Notice that as we move around this square in this counterclockwise direction, we also move around this region R in the counterclockwise direction. Next, we're going to introduce a new definition called the Jacobian. Now, if we have a transformation T given by x equal to a function of u and v, y is a function of u and v, then the Jacobian of the transformation is given by this determinant of this 2 by 2 matrix, with the first row here consists of the partial derivative of this function with respect to u, and then partial derivative of this function with respect to v, and then the second row will be partial derivative y with respect to u, partial derivative y with respect to v. The determinant of this matrix is called the Jacobian, named after a German mathematician, Jacobi. Jacobi was the first Jewish mathematician to be appointed professor at a German university. The crater Jacobi on the Moon is named after him. Now let's look at one example to understand how to compute Jacobian. For example, the transformation from the R data plane to the XY plane is given by these two equations. The Jacobian of this transformation T is the determinant of this matrix. The partial derivative x with respect to R is equal to cosine theta. The partial derivative x with respect to theta is equal to negative R sin theta. Is equal to negative R sin theta. The partial derivative y with respect to R is sin theta. Partial derivative y with respect to theta is R cosine theta. Calculating, the determinant of this matrix is R times cosine squared theta plus R sin squared theta, which is equal to R. After introducing the definition Jacobian, we're going to introduce you to this theme here. Change your variables in a double integral. Suppose T is a C1 transformation whose Jacobian is non-zero, and T map a region S in the UV plane onto region R in the XY plane. Suppose a function f is continuous on this region R, and R and S are of type 1 or type 2 plane region. Suppose also that T is, this transformation T is 1 to 1, which means that there's no two points in this region S that map to the same point on this region R. Then we say that T here is 1 to 1, with the exception that perhaps on the boundary of this S, that T doesn't have to be 1 to 1. Then what happened here is this double integral of this continuous function f on the region R is equal to the double integral of this function f as a function of, you're going to express the x over here in terms of u and v, and then the y over here in terms of u and v, and then multiply here by the absolute value of the Jacobian of this transformation, and integrate it over this region S over here on the UV plane. So a couple notes over here. First, what does it mean, a C1 transformation? Basically, it just means this two function where x and y expressed as function of u and v, they have continuous first order partial derivative. Now, R and S are of type 1 and type 2 plane region. Let me remind you, type 1 region, the region is being bounded above and below. So this is a type 1 region. Y go from G1 to G2. x go from A to B. This is a tighter region. X is bounded on the left by H1, bounded on the right by H2, and Y go from C to D. And the next note over here, we're going to give an example of this theme over here. So we call that polar coordinate transformation that transform this region on this R data plane to this region on the XY plane. And that transformation is given by x equal to R cosine theta, y equal to R sine theta. According to the theme above, this double integral over this region R on this xy plane is the double integral. We place x here by R cosine theta, y here by R sine theta, and then multiply by the absolute value of the Jacobian, well, which we already computed in this example. The Jacobian of this transformation is equal to R, and R is positive. So the absolute value of this Jacobian is equal to R. And then du dv here is dr d theta. Now this equal to this is the same formula that we have used when we do the conversion of this double integral over a rectangular coordinate to this double integral using polar coordinate. It's the same formula in section 15.3. Now let's look at example 2. We want to use this change of variables x equal to u squared minus v squared, y equal to 2uv to evaluate this integral where R is the region bounded by the x-axis and y squared equal to 4 minus 4x and y squared equal to 4 plus 4x and y is greater than or equal to 0. Now notice that this region R is the same region in our last example. It is the image of this region S, this square over here on the UV plane under this transformation. Let's compare this region S and region R. Region S is much simpler than this region R. So the first step here is to find the region S. The next step, we're going to compute the Jacobian. Taking partial derivative x with respect to u, partial derivative x with respect to v, we get 2u here and negative 2v here. Taking partial derivative y with respect to u, and then partial derivative y with respect to v, we get 2v here and 2u here. Calculating the determinant, we get 4u squared plus 4v squared. We know that this is a positive quantity. So now we can apply theme 9. We got this region S. We also compute the Jacobian. So the function we integrate with is y, and y is equal to 2uv. And then here, multiply with the absolute value of the Jacobian, and then integrating over the region S. Notice that S is simpler than this region R. Now we set up this integral. U here change from, well, looking at this region S here, you see that U, this is a square. U go from 0 to 1, and we go from 0 to 1. So U change from 0 to 1, we change from 0 to 1. After that, we can distribute and simplify, and calculating, do the inner integral first, and then later do the outer integral next. We're going to get this result, and the result is equal to 2. So using this change of variable theme, we're able to compute this integral much simpler. So let's go back and think about what we have done and what are the steps in solving this type of problem. So we're given this integral over here where the region that you integrate over is a little bit more complicated. Then what do we do here? We use the change of variable theme, change of variable for double integral theme to do this. In this theme here, we need to first find out this region S, and this region S should be simpler than this region R. So that's the first step. The second step, we need to compute the Jacobian of this transformation, and then take the absolute value of that. And then step 3, we're going to apply the theme once you figure out the S and the Jacobian. Notice that this problem over here, example 2, is not too difficult because the transformation T is given. So you don't need to figure out these 2 equations for the T. Now, if you're not surprised with a transformation T, and we need to add one more step before we go through the problem. So we need to think of an appropriate change of variable before we proceed. Now, to help you with how to think of an appropriate change of variables in double integral, I have made this video with example and post it in my channel. Okay, the next example, evaluate this integral where R here is this region like a trapezoid with vertices here, 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 and here. Look at this. Let's look at this function that we integrate. It is difficult to integrate this function. So we want to make this function we integrate turn into a simpler function. So the first step, we'll think of a change of variables to make this function simpler. So looking at the form here, and that would suggest we should maybe let u equal to x plus y and let v equal to x minus y. And this is a transformation from the xy plane to the uv plane, which is the inverse of t, because t supposed to transform a region at the UV plane to XY plane. Now, if we know the inverse, then we can solve for x and y, express x and y in terms of u and v. Then this change of variables would define this transformation t. The second step is to compute the Jacobian of this transformation t. Calculating the Jacobian here, we got -1/2. The next step is to find the region S in the UV plane. This region here at the XY plane, the boundary of this region is going to map to the boundary of this region at the UV plane. To find out this region here, let's consider each side of the boundary. R1 over here, x go from x is greater than or equal to 1, less than or equal to 2, y equal to 0. Substituting y equal to 0 here and here, we get u equal to x, v equal to x. Eliminating x, we got v is equal to u, where u and v are greater than or equal to 1, less than or equal to 2. So v equal to u is this nice segment here, where u and v greater than or equal to 1, less than or equal to 2. So R1 and here is S1. The R2 over here is the equation for this line here. Notice that if you know the x-intercept and the y-intercept, you can write out the equation of this line. It is x minus y equal to 2. And remember, x minus y equal to v. So this one here is v equal to 2. So v equal to 2 is the corresponding equation for that line segment on the UV plane. So v equal to 2 is this horizontal line, and this line segment is going to start from here and then end it when u equal to -2, because here x equal to 2, y equal to 0, so is this point is going to correspond to this point here, and this point over here, x equal to 0, y equal to -2, so u equal to -2 is this point, u equal to -2. So end it over here. So u is, so v equal to 2, and then this line segment will go from here and then end it over here, going this way. Okay, R3. R3 is going to start from here to here. And you see that x is going to equal to 0, and y is greater than or equal to -2, less than or equal to -1. Substitute x equal to 0, u is equal to y, and then v is equal to -y. Eliminating the y, we get v equal to -u. And notice that u here is equal to y is greater than or equal to -2, less than or equal to -1. So u is between -2 and -1, including this 2n. V equal to -u is this nice segment here, with u go from -2 to -1. And the last side here, R4, the equation for this line using this two intercept here, we got the equation of the line is x minus y equal to 1. Notice that x minus y equal to v, so this is v equal to 1. So v equal to 1 is the equation of this, and it's going to start from this point and end it at this point. So putting all this together, we get a trapezoid here. Notice that this region here is moving. The boundary here is moving in this clockwise direction. And then this region over here is moving in this counterclockwise direction. This region over here, this S here is simpler than this region. And it is a title region. And U is bounded on the left by this, bounded on the right by this. So U is bounded, U is greater than negative V and less than V. And V is greater than equal to 1, less than equal to 2. So it is a title region. Next step, we're going to apply the theme. So we got S, and we got the Jacobian. Now we're going to apply the theme. So the function we integrate with is this function. We're going to express this in terms of u and v. So this is u, this is v, so this is u over v. The Jacobian of this we calculated already. It is 1/2. The absolute value of that is also 1/2. And then integrating over this title region. So title region, we integrate with respect to u first. You go from negative v to v. And then integrate with v after. We go from 1 to 2. Evaluate this double integral, we got this result. Notice that using this change of variables in double integral, we're able to evaluate this integral that's a little bit difficult to integrate and change to in the integral that is much simpler to integrate. And we got the result. So the one we have just gone over is change a variable in double integral. Now what about triple integrals? We have a similar formula. First, the Jacobian of the transformation T is given by the determinant of 3 by 3 matrix, with the first row here being the partial duality of x, first with respect to u, and this is with respect to v, and this is with respect to w. And this is partial duality of y with respect to u, and here v here and w. Partial duality z with respect to u, with respect to v, with respect to z here. And this is the Jacobian of the transformation T. And the change of variables in triple integral formula is this one over here. Now this function here is going to be a function of 3 variables, and the Jacobian here will be defined by this, and then du, dv, dw, and it's going to over a solid. Okay, so a solid in the UVW coordinate. This is a solid in XYZ coordinate. Now just one more example. to see how we use this change variables in triple integral. In this example, we're given this change variables and it defines this transformation from a raw data file coordinate to XYZ coordinate system. You first compute the Jacobian by taking partial derivative of each one of this with respect to row, with respect to data, with respect to phi, and then calculate the Jacobian, and it turned out to be negative rho squared sine of phi. And because phi is between 0 and pi, sine of phi is greater than or equal to 0. So the absolute value of this Jacobian is going to be rho squared sine of phi. Now using the formula there, we're going to this triple integral over a solid R is equal to a triple integral. We place x here by rho sine phi cosine theta. Y we place by rho sine phi sine of theta. And G we place by rho cosine of phi. Absolute value of the Jacobian is rho squared sine phi, which is this one over here, and then d rho, d theta, d psi. As many of you have realized that this is the exact formula when we change from a rectangular coordinate system to the spherical coordinate system for triple integral. This is the same formula we have used before, right? So this concludes the end of section 15.9.